Chapter 17 is the first chapter on the phenomenon of light and the various properties associated with it. In this chapter, I will discuss mainly the law of reflections and the three types of mirrors that exist, those being the flat mirror and concave and convex mirrors. Light is a phenomenon we are all familiar with. Life on Earth depends on the light that the sun emits, and that light carries thermal energy, which warms up our planet and provides all the energy for living organisms to thrive. Historically, light was studied by observing the shadows that objects cast when illuminated by a light source. There are two types of light sources in existence. We have natural sources of light, and we also have artificial sources of light. Natural sources of light are the sun and stars, candles, fire, or any object that can be made to burn with flame by being heated above certain temperature. And artificial sources of light can be light bulbs, fluorescent lights, or the moon, which reflects sunlight. So natural sources of light produce their own light, and artificial sources of light cannot produce their own light. They are working on some other principle that results in production of light. Shadows are formed by blocking the light from a source and thus forming an image of the shape of the object on a screen. When a point source is used to illuminate an object, the object is going to block the light coming from the point source, and then on the screen behind the object, we are going to see the shadow cast by the object, and that is the portion of the light coming from the source that's being blocked by the object itself. Now, this is an idealized situation. In reality, there are no point objects of light. A more realistic object will be, a more realistic source of light would be an extended source of light, such as a light bulb or a lamp of some sort, or the sun, or a candle, or any real source of light. When the light is cast upon our object, again, a shadow is formed behind on the screen, but as you can see from those two examples, the shadow cast by the point source is very sharp, while the shadow cast by the extended source is not sharp at all. The shadow cast by the extended source has two regions in it. It has a central dark region, which is called umbra, and then it has a lighter peripheral region, which is called penumbra. So the central dark region is umbra, and the peripheral less dark region is penumbra. So from the behavior of shadows cast by light sources, people have determined that light travels in straight paths when emitted from any source. And so for convenience, a beam of light is represented as a collection of parallel light rays, and the direction of propagation of the beam and those light rays is indicated by an arrow. Imagine that this is the beam of light. It is coming from a source on the left here. For example, this could be a laser of some sort. So this beam is a collection of light rays. And so the light rays are indicated as thin straight lines, which are all parallel to each other. Since the light beams propagate along straight lines. And to indicate the direction of propagation, we use arrows. And so those are the light rays from which the beam is made. So when we are talking about the light that is emitted by a source that illuminates an object, and then we are talking about the image created by that light source and the object, I'm going to discuss the paths that the light rays in a beam take. So in this sense, I can even discuss the paths of individual light rays, and assume that that is the behavior of all light rays in that particular light beam. So in future discussions about the properties of light, we're going to talk about light rays and sketch individual light rays instead of entire light beams. But we will understand that those conclusions that we will reach apply for light beams in general. Light that strikes most objects leaves in a great many directions. And this must be true because we can see the object from many different viewing directions when the object is illuminated even by a single source of light. A way to obtain an image of an object illuminated by a light source would be to place a photofilm in front of the object so that the object is between the light source and the photofilm. Now, due to the fact that light that hits the object will reflect in all directions, there will be no real image created on the photofilm. However, there is a way that an image can be created by applying certain conditions to the light rays that travel from the object after reflection towards the photofilm. And so a simple device that can achieve those conditions is the pinhole camera. So here is the setup that a pinhole camera provides in order to get an image of an object illuminated by a light source on a photofilm. As I mentioned already, if we place our object, which is a vase with some flowers in it, in front of our photofilm, when this object is illuminated by a light source, the light that's reflected from the object will be reflected in all random directions, which then results in no actual image created on the film. However, if we place a screen between the object and the photofilm, and then we cut a small hole in the screen that is going to filter only the light rays which propagate in such a direction that they can pass through this hole and then will be registered by the photofilm. And so when the light rays coming from all parts of the object pass through this pinhole, and again, those will be only the light rays that are traveling in the correct direction so that they can pass through the hole, we get a collection of images of the various points of the object, and that collection will be the image of the object. Now notice that this image here is not very refined, and that is because of the size of the pinhole. As a matter of fact, this is not really a pinhole, it's a larger hole. So if the size of this hole is reduced to a pinhole, so a tiny hole, like this one, then that is going to even further reduce the number of light rays that can pass through that hole, which then is going to create a more refined image on the film, but at the expense of contrast. So the image will be much dimmer compared to the previous example. So this simple device operates based on the principle of reflection of light. Now let's look at that a little bit more depth. We see objects around us due to the light reflected from them. The light rays reflected propagate in different directions after reflection, and they are no longer parallel to each other as before the light hit the object from which it reflected. The reason for this diffuse reflection is the unevenness or the roughness of the surface of the object. And so because of that, it is possible to see the object from different positions around it, again, even if it was illuminated by only one source of light. And so here is a drawing of a light beam made of multiple parallel light rays that hits a surface that is not perfectly even. And so after reflection, the light rays will go in all kinds of different random directions. And so for an observer that is located somewhere here, the light rays that hit the observer's eye will then basically produce an image for the observer of the surface. For an observer that is right here, the light rays reflected in that direction that enter the observer's eyes will produce an image of that surface here, but some at that location, and so on and so forth. So then, how does the law of reflection? How are reflections formed? Is the question. Experimentally, it was determined that any light that reflects from any surface does so according to the law of reflection. The law of reflection states that a light ray incident upon a smooth reflective surface will reflect at the same angle as the angle of incidence. So let's take a plane or flat mirror as our reflective surface, and then let's shine an incident light ray at a certain angle called incident angle. This angle is measured from the line, which is fictitious line, which is perpendicular to the surface of the mirror. And then if we measure the angle at which the light is reflected, again with respect to this imaginary perpendicular line, perpendicular to the surface line, then the angle of reflection will be equal to the angle of incidence. So one more time. Here is our reflective surface. This is a flat mirror. So the incident ray is reflected from that surface. The angle at which the ray hits that reflective surface, I'm going to call angle of incidence or incident angle. And this angle is measured from this imaginary perpendicular to the surface line, which we call the normal. Then the angle of reflection or the reflected angle is measured from the reflected ray to the imaginary perpendicular to the surface line. And so those two angles are equal. The incident angle is equal to the reflected angle. And that is the law of reflection. Let's use symbols for those two angles, which is going to be easier to do sketches for situations where reflections are present. So let's call the incident angle theta sub I, and let's call the reflected angle theta sub R. So theta sub I is the incident angle, and theta sub R is the reflected angle. And so then, in those terms, the law of reflection simply states that theta sub I is equal to theta sub R. And so here is a picture of an actual experiment where different colored lights were shown upon a flat mirror. And as you can see, they are reflected at the same angle as the angle of incidence. And these angles again are symmetric with respect to this imaginary line that is perpendicular to the mirror surface. And so going back to the diffuse reflection discussion, the incident light ray is made of the incident beam is made of those parallel light rays, but because they hit these uneven parts of the surface at essentially different incidence angles, then they will reflect according to the law of reflection at different angles of reflection, and so that will result in the beam diffusing after reflection. Mirrors are devices that operate on the principle of the law of reflection. Mirrors form images through reflections, and there are three types of mirrors based on how they form reflections or images. So the three types of mirrors are flat mirrors, convex mirrors, and concave mirrors. So let's look at these three types of mirrors, and let's see how images are formed when light reflects into those mirrors. For any of the three types of mirrors, for an observer to see a reflection of an object in the mirror, the reflected light rays must enter the eyes of the observer. So let's start with a simple example of a point object located at point P, which is illuminated by a light source. So when the light from the light source hits the object here, the light will be reflected from the object, and it's going to travel down those two paths. And of course, this is only two light rays from the reflected light, not all of them. So when this light ray hits the mirror at point A, it's going to reflect, and it's going to end up at point B. Okay. If I continue the beam behind the mirror, so this is not a real light coming from behind the mirror, we just imagine that the beam is continued behind the mirror, it's going to pass through point Q. Well, point Q is also defined by this other light beam, light ray, which is reflected at point D and goes this way, but when continued behind the mirror, it's going to intersect with the other imaginary beam behind, with the other imaginary ray behind the mirror at point Q. So again, we have a light ray that starts from point P, hits the mirror at A, and reflects towards B. We have another ray that starts at P, reflects from the mirror at point D, and then ends up at point E. Those two light rays, if continued behind the mirror, are going to intersect at point Q. So, for an observer that is located at point B or point E, it will appear as if the light is coming from point Q, or in other words, for an observer at points B and E, it would appear as if the image of P is behind the mirror and at point Q. So now let's sketch in a different manner the formation of an image by a flat mirror for an observer. So here is my flat mirror. This is the back of the mirror that is not reflective, and this is the front of the mirror, which is reflective. So let's place an object in front of the mirror. So here is my object, and I'm going to use a simple arrow to indicate the object. Let's illuminate this object with light, and let's look at two light rays that are reflected from this object. Light ray number 1 is reflected from the very tip of the object, hits the mirror, and then according to the law of reflections, the angle of incidence should be equal to the angle of reflection, and so therefore, after reflection, the light ray passes in that direction. The second light ray is the one that's reflected from the bottom of the object. So it hits the mirror here. Again, according to the law of reflections, the angle of incidence is equal to the angle of reflection, so the light ray will reflect and travel in that direction. The two light rays will converge right here, and if we place an observer in that particular location, they will be able to see an image for this object. But for this observer, where would the image appear to be? The image will appear to be behind the mirror. So how do we then form the image of this object behind the mirror? Simply continuing the two light rays along the same direction that they were traveling towards the observer, but behind the mirror, will essentially locate the tip of the image and the base of the image. So we continue ray number 1 along the same direction. It was traveling this way, but behind the mirror. And then we will continue ray number 2 along the same direction, but behind the mirror. And so that defines the positions of the tip of the image and the base of the image. And then the rest of the image can be built by using, all the rays that are reflected by the object that hit the mirror and then reflect towards the observer. We continue them behind, and that's how we build the image. So this image actually doesn't exist behind the mirror. Why? Because the back of the mirror is not going to be transparent for the light. Light doesn't pass behind the mirror. And because of that, this image not being actually real, we call the image virtual. Again, this image cannot exist behind the mirror, but it appears as if it is behind the mirror. And because of that, this is called a virtual image. Another thing of note is that the distance between the object and the mirror is equal to the distance between the image and the mirror. So the object and the image are located equal distance from the mirror on each side of the mirror. Another thing is that for flat mirrors, the size of the object is equal to the size of the image. Or in other words, flat mirrors do not magnify. They have no magnification. So let's summarize the rules for a flat mirror. Number 1, the image created by a flat mirror is virtual. So again, it physically cannot exist behind the mirror, but it appears as if the image is behind the mirror. Number 2, the distances from the object to the mirror and from the image to the mirror are equal. And number 3, the image and the object are the same size. One last thing to note about the images formed by flat mirrors is that a flat mirror forms an image of an object even if the object is not located directly in front of the mirror. All that it takes for this image to be seen is for the observer to be at the correct position so that the reflected from the mirror light rays that are coming from the object fall onto the eyes of the observer. So if the observer is at a position where the light rays coming from the object and reflected from the mirror do not fall onto the eyes of the observer, then the observer will not see the image.